Hey everyone, welcome back to day 51 of Coding Every Day. So today I'm going to do something a little bit different. Um, so it's been 50 days, so I want to take today to kind of just reflect on my progress over these 50 days. So I'm going to do that by just trying to get through a bunch of easy problems on LeetCode and see if I find them easy or kind of where I'm at with that. So today's a Friday. It's a spring day in March. Spring's coming, so yeah, so I'm just going to do as many of these as I can for a little bit and just kind of see how it goes. So, yeah, looking forward to this. So, we'll start with number 26 remove duplicates from sorted array. Okay, given an integer array nums sorted in non decreasing order, so increasing, remove the duplicates in place such that each unique element appears only once. The relative order of the elements should be kept the same. Then return the number of unique elements in nums. Consider it to be k. The number of unique elements to be k. To get it accepted, you must change the array nums such that the k first element of nums contain the unique elements in the order they were present. The remaining elements of nums are not important, as well as the size of nums. Okay, so that kind of makes me think. So because it's sorted, we'll know when we have duplicates because we can, we have I, and then if I ever equals I plus 1, then we know that we have a duplicate. So we'll keep going until I and I plus 1 are the same. When they are the same, I think what we should do is probably swap I plus 1 with I plus 2. So then we'd have 1, 2, 3, 2. Well, we want 2 to just like go to the end. So ideally this, we would want it to be 1, 2, 3, 4, 5, 2. So would we do 1, 2, 3, 2, 4, 5, and then so I would, so I was here and we swapped I plus 1 and I plus 2. What we could also do is I keeps going and we keep track of the previous value, and then once we encounter it again, then we swap. So we would stop when I is here, and then we would swap I with I plus 1. Which would then give us this array here, and I would be here. So we swap, and then we increase. So could we keep just swapping? Well, we have to remove. Okay, we don't. Okay. So we don't actually remove the duplicates. We just have to put them to the end. So we could shift everything. So we could just like say this goes to the end and everything else gets shifted, but that would be O of n to shift everything like that. We could also use like a linked list maybe. So that way, that might be good if, so instead of this 2 pointing to the 2, we can just make it point to the 3. But we're given an array and we should return an array. Okay, so it doesn't matter what these equal to. So what if we just kind of continuously swap? So then, hey, we'd see So we would move I here, and then we would see, okay, so maybe instead of just checking if it's the same element, we can check if it's the same, or if the element to the left is less. Not if it's a less than. So how do we know that this 2 is bad? Should we just make it like a -1? Do they have to be positive? Nope, doesn't have to be positive. So we could maybe make it like a number that's unreachable, like -101 or something. I'll just say x, and then we can, this doesn't seem like it would be right, but we can check if it's an x, and then we can swap them. And then we go up, and then we check if it's an x, we can swap them. But what if we had like another 5 here? So if we had x55, then we would swap them, and then we would never know that the 5s were next to each other. So all right, let's go through another example. Keep brainstorming here. So 0, 0, 1, 1, 1, 2, 2, 3, 3, 4, and this should go to 0, 1, 2, 3, 4, and then it doesn't matter how many elements are here. The size of nums also doesn't matter. Okay, so let's start with just the trivial solution. So the trivial solution would be you loop through it. So you loop through it, and whenever I equals I plus 1, then you just remove this from the array. Then you go, I equals I plus 1, so you remove this. And I guess you would just like keep checking and keep removing. Okay, and now it doesn't, so then we increment I. It does, so we delete that one. It doesn't, so we increment I, right? So we can do that. The problem is with that, so I would go from the left to right, so that would be n, but every time we remove an element, that's also n. So we could remove n elements, which would be n squared. So that would be the trivial solution. So I'm thinking there has to be some algorithm where we can either swap numbers or move them somewhere so that we know, we can just kind of get rid of them. All right, I don't need to rewrite it. So as a human, when I look at this, I see, okay, 0 and 1 are different. So this part of the array is completely fine. Here, I see, okay, these are the same. So we want to get this one all the way to the end. So we could keep swapping it. And I have to do it in place as well, because so another way you could do it trivially is if you don't do it in place, you could have another list and just add to it whenever you encounter a new element, like this. And then this would just be your array. So you could keep a set as well. Yeah, so how could we move? So I guess what we'd want to do is swap So what swaps do we want to make to get to our solution? So we probably would want to, so 0 will stay the same. This 1 will be fine. We want to swap these two. 2, 1, 1, 2. So we swapped these two. What about this one? We just want these to disappear. So can we just put them to the end? I feel like that's tricky because if we put them to the end, like something has to take its place. I mean, okay, so I think I know a way we can do it maybe in 2 pass-throughs. So the first pass-through, we can just keep track of like all the unique elements. I'm allowed to do that, right? So what if I just pass through and add everything to a set? 0, 1, 2, 3, 4. Okay. So then I loop through this array, so that the original array. And I say, if this is in the set, so okay, so we'll encounter a number. So we'll say, is 0 in the set? If it is, we won't do anything, and we will pop 0 from the set. Then we'll go on. Is 1 in the set? Yes. So that means we won't do anything, and we'll pop this here. Okay, then we get to 1. So 1 is not in the set. So we need to replace this with the next biggest. So what if we used, could we use a stack somehow? So we kind of want to pop from our stack. So ideally we want 0 at the top, then 1, and then 2, and then 3, and then 4. And then but we need to know. So we have to know that, and they don't have to be, yeah, it doesn't have to be, like it could skip. So it could be like 0, 2, 5, 7, 8. So I'm thinking so we could check, hey, is 0, oh, I guess we could check if it's the top of our stack, which is O of 1, instead of if it's in the stack. So we can say, is this the top element of the stack? If it is, then we do nothing to the list, and we move on, and then we pop this from the stack. Okay. Then we say, is this the top element of our stack? It is. So then we move on, pop that from the stack. Then we say, is this the top element of our stack? It's not. So we make this element the top element of our stack. 2. So then we'd have 0, 1, 2. And then we would pop 2 from our stack. Then we say, is this the top element of our stack? No. So then we would pop from our stack and make it. And then here, is this one? No. So then, So this is it seems really simple. And maybe it's just me not being used to doing easy problems, but is it just that simple where we can loop through here and every time we encounter a number that's not in our stack, we just push it? So building the stack, because if we have the stack, we can easily just keep popping from it. So what if we have 4, right? So we have our stack and we say, hey, is this the top of our stack? No, so let's add it. Is this the top of our stack? No, so let's add it. Is this the top of our stack? Yes, so we don't add it. Is this the top of our stack? No, so we add it. Is this the top of our stack? Yes, we don't. So then we can just build it like that. And then we have the problem. Okay, so I guess I could use a stack to do this. Okay, so let's try it like that. So I'm going to loop through it backwards. And I'm going to say, so for I in range, length of nums -1, -1, -1. So that'll loop through it backwards. And then we'll have our stack. So this first pass through will build the stack. And then second pass through will use stack to alter nums. Okay, so we're going to say if nums of I, so if it doesn't equal the top of our stack, then we'll add it to the stack. And if it does, we'll just do nothing. So that should build the stack. And then we'll go through it forwards. And we'll say, so what did we say again? We said, if this, so at every step I remember we pop from the stack. But I wanted to try, so, okay. Well, can't we just say that nums of I equals stack.pop? Like this. And won't that like just work? It's gonna, I'm not returning anything, but I just want to see the list index out of range. So this is an index error, right? Because it has no element in it. So if stack so if it's empty, or yeah, because if it's empty, that's the same thing as not, we should add it. And then we're popping from an empty list here. Line 12, 30, okay, 12. So we are popping. So maybe what we want to do instead is range length of stack, because that will be k. Okay, I thought this was fine. I thought I'm supposed to submit. Okay, and what do I return? K. So here I'll just say k equals length of stack. And then try in range k. And then what? I'm supposed to return k, and then it's going to check, right? Return k. Yeah, okay. And then it basically just only gets the last of them. Okay, sweet. So that took me longer than expected. You probably don't, this is probably overcomplicating it. It's definitely overcomplicating it. It's just like, so for me, you can, so this basically gives us the unique elements and then tells us the order that we need to add them. So that's why I did that. And then so when we pass through, it's like, we can just do it. All right, we could go on to the next problem. All right, let's look. Sorry, I had to sneeze, but it went away. Okay, so that was problem number 26. Okay, now we'll look at remove element. Okay, I can't believe they put all this stuff. Given an integer nums, a list of nums and an integer val, remove all occurrences of val of nums in place. The order of the elements may be changed, then return the number. So it's very similar to the last problem. So do we have a test case? Yeah. Okay, so it looks really similar. So basically we have to remove everything that has 3 in it. Here we remove everything that has 2 in it. So we could solve it the same way, where if it doesn't equal, so we could do it the exact same way, where we go through from the right and add everything to the stack that isn't a 2, and then we can go through the left and just change it in place. I feel like there's definitely a better way to do it though. So yeah, so in this case, I'll just write it. So if we have 0, 1, 2, 2, 3, 0, 4, 2. So we would go through this way and we'd say, okay, this equals the target, so we're not going to add it. And then we'll do 4, 0, 3, 1, 0. And then we would basically just go through this and then change every element, 0, 1, 3, 0, 4, and then whatever this is doesn't matter. This one changed the order though. Yeah, so if the order doesn't matter, is there a way we could do it in just one pass through? Because I feel like, all right, so when we encounter a 2, we need to know what value to replace it with, but we haven't even got there yet. So, I mean, we could do something like, so it's like, okay, we have position 2 and position 3 need to get replaced. When we encounter a non-2, we swap it with position 2. But then that means that this position needs to be replaced. I mean, this could work. This could work, actually. This could work. And I guess it would be in one pass. Okay, so we're going to keep track of the positions that need to get swapped with. So, I don't know. I'll just call it like P. So we'll have I goes here, that's good. I goes here, that's good. I goes here. This is the target, so we need to swap something with position 2. And then here, I goes here. And then, okay, this is not good either, so we have to swap something with position 3. Then we go here. And I guess it doesn't matter if we use a queue or a stack here because we have to swap all of them anyway. So then we would swap. So we put 3 here and 2 here, and then we would add. So we would get rid of 2, but we would have to add 4 now as something that needs to be swapped with. And then we could go I is here, so this is something that we can swap, so we can swap these. And then we add position 5 and get rid of position 3. We go here, and then, okay, we can swap these two and add position 6, but get rid of position 4 here. So we can't swap it. So then I will reach the end. And then we can define k as the length of this minus the length of p, because that would have added 7. Okay, that seems like it works, and I think it'll work too. I was gonna say it might work as a stack, but I don't know actually. Let me just quickly do it again with the stack. So if we have 0, 0, 1, 2, 2, 3, 0, 4, 2. Okay, so and then P. Okay, so I's, this one's good, this one's good, this one's good. So we'll add it to a stack now. So index 2. Then we'll add this to a stack, index 3. Then we'll swap it with the top of the stack. So we'll swap these two. Then this will become 4 goes to the top of the stack like this. We see this, so then we'll swap this one. And now this will get replaced with 5. Then we see this one. Yeah, okay, it looks like we do need the queue. So then these would swap. Yeah, okay, so we'll just do the queue idea. Because it kind of looks like bubble sort, I think. But if we do it the other way, then I think that's better. So we'll have, let's have a queue. And then we'll say, so I'm going to have just P. Well, that's not really that descriptive of a variable. So what could we call it? Like needs to swap. And that'll be a list. So this is a queue. So this is a queue. And then we're going to say for num, so let's say while I is less than length of nums, we're going to say, so there's 2 things. So if nums of I does not equal value, then and needs to swap has at least 1 element. For clarity, I'll say, actually I'll just call it Q now I think about it, and that'll make it more readable here too. Okay, so and our Q, it has at least 1 element. Then what we're going to do is Q dot pop. So this will be the position. So we want to swap our, so we want to say so let's say we've encountered here. So we want this value to go to the target position. So we'll say nums of index equals nums of I, and then nums of I would be equal to val. And then obviously, of course, we would have to add a temporary variable, but I just want to make sure this logic is right. So nums of I should be equal to the value. Okay, so then does this work without the this might actually work just like that. Okay, so we'll swap them. Otherwise, if it is a value, then we'll say q dot append left I. Okay, and then let's return the length of nums minus the length of q, like this. I never initialize I to be 0. Let's try again. So my output is 1, 3. So after every step, I'm going to print nums. Okay, so this is after we went to 0. So why does 0 get? Oh, I see. I'm missing else. Okay, let's see if that fixed anything. Okay, now we failed the original case. Could it be this? So in the queue, so if the queue is empty, all right, let's see. I think it could just have to do with the logic there, with the queue being empty. So yeah, so this gets identified as a problem. So then when we encounter this 2, we switch it. And then we go on. This 2 is fine. Okay, let me also, so let's say swapped. So we're swapping nums of I and value. I also want to print the q at every step as well. All right. So our dex starts with 0 in it. Yeah, that makes sense actually. So we actually want, I think it's just the logic here. So we want to say if q, like that. So if they're not equal, that means we should swap. But if there's nothing to swap with, then we don't swap. But we also don't append to the queue either. So why is 0? So 0 is getting added. Okay, so 0 is getting added because index 0 is a problem. So then we swap 2 and 3. And then we encounter, so we swap 2 and 3. And now our queue is empty, so we don't do anything. Oh, it's because after I swap, I'm forgetting to add that position back into the queue. So I did that in my algorithm. So what you have to do is you have to add this position back in anyway. Was that what was causing it? Okay, let me see if it gets submitted. All right. Okay, so it's basically, all right, so that was exactly what I had on the whiteboard. I just didn't code it correctly. Also, this doesn't seem great logic here. So we'll say if nums equals value, then, well, okay, so the only time we don't want to add it to the queue, so if nothing's in the queue, because this gets added either way. So I think what we say is, all right, so what am I doing? So I just noticed that we have this code twice, and I want to reduce it. So nums of I does not equal value. Okay, so if it's a normal number, that means we want to swap, but only if, yeah, so then we want to swap. Okay. And all of the time, we want to add the number. Unless the queue is empty. Okay. Maybe we could say here. No. What's the best way to logic this? So we have like the queue and then is val. Okay. So if the queue is empty and it's the value, then we just add to queue. That's it. If the queue is empty and it's not the value, then we do nothing. If the queue is not empty, so there's something in the queue and it is the value, we add to queue. It doesn't matter. Whenever it's the value, we must add it to the queue. If the queue is not empty and it's not the value, we swap and then add to queue. Okay. So using this truth table, we know that if nums of I equals the value, we're going to add it to the queue, the index, no matter what. So that's this. Okay, otherwise, if it's not the value, we have to check we have two conditions. Okay, so in this case, we should do nothing. So I'm only going to do this. So if the queue is empty, then we have to swap. We have to swap. Well, actually, okay, so if we're in the else, that means we're in here. And then we can use the and to restrict it to this box here. But the problem is we also have to add it to the queue as well. So do we say that? So if it's this or the queue is empty. Okay, let's see if that works. Okay, it did not. It did not work. So we could also think about it like this. If the queue is empty, we're always going to add to the queue, right? No, that's not even true. Is this even true? Oh, this is... Oh, false means it's not empty. Okay. So this means it's the value. Or it's not empty. Okay. So if it's the value, we must add it to the queue. Is this truth table even correct? Honestly, I feel like at this point the stack would have just been better. All right. Let's think. So if it's... The easy one to me is if it is the target value, you are going to add it to the queue no matter what. So let's just think of like a human approach. So if it's the target value, you're going to add it regardless of whether the queue is full or not. If it's not the target value, you're only going to add it if the queue has something in it. So what you'll do is so do I have to have it down here as well? So we're going to swap. And then add it. Okay. So if it is the value, we're going to add it to the queue. And that's all we do. If it's not the value, there's two cases. Either the queue is empty or the queue is not empty. If the queue is empty, we just continue and do nothing. So in this case, it's not the value, it's not the queue, so we'll just continue and do nothing. If it is, if the queue, so let's say we get to 3 and the queue has something in it, then we swap the values and then add I to the queue. So that looks like what I'm thinking. Okay. I think it was just the print statements before that were dragging it down. I think it's like the exact same thing. And then we can just do it like that. And can I not? So if I do this, it breaks it. Yeah. I see, because I was just, yeah. So this will, it will add its value regardless of if it even matches or anything like that. But there is some cases where we don't even, so you might say, oh, well, both of these, so shouldn't we just add it here? Well, no, because there's some times where we actually don't want to add it. In the case that the queue is empty and it's a non-target value. So that being said, that is this problem. So that should work. Yeah, so I don't know if I'm just like bad at LeetCode or something, but or if I'm just thinking about these problems too hard, but I am, I am having to think. They're not as automatic as I was expecting today. Okay, so we've done 2. Yeah, I wonder if you could do this one in a similar way, but okay, so now let's look at problem 28. Find the index of the first occurrence in a string. Given 2 strings, needle and haystack, return the index of the first occurrence of needle and haystack, or -1 if needle is not a part of haystack. Okay. So this to me seems like a sliding window problem. So what you do is you just have a window of size 3 and you just keep checking if that window equals the value. That would be the easiest way to do it. String, okay. So I think I'll just do that. So that would be, so a sliding window is, so the runtime of that is n minus k plus 1, where k is the size of your window. And then for every window, we are going to search k times. Because to compare 2 strings of length k, you must do k operations. Yeah, so I think I'll just have a function that manually does it. All right, so first we'll generate all windows. So we'll say, so I'll set k equal to length of needle. And then I'm going to say for I in range, so we want to go from 0 until length of haystack minus k plus 1. And then I want to print haystack from I to I plus k. Okay, sad looks good. So sad, ABD, DBU. Okay, so then we want to, so we'll say, we could say here, if haystack of I to I plus k equals needle, return true. What do we return? Oh, the first occurrence. So we'd return I. And then if we get to the end, we'll return -1 like this. So this should work. Okay, I guess it beats 100%, so we'll just leave it at that. I didn't know if there was a better way to do it, but all right, so we'll leave it there. Basically just a simple sliding window problem there. All right, LeetCode.com/problem set. So that was problem number 3, right? All right. So now let's go to problem 35. This one has a lower acceptance rate. Search insert position. Given a sorted array of distinct integers and a target value, so unique integers and a target value, return the index if the target is found. If not, return the index where it would be if it were inserted in order. Okay, so we basically just binary search. All right, so let me write a binary search. So in a couple videos ago, I had to write a binary search for something and I messed up a little bit, so I'll share with you. So we set L equal to 0 and R equal to length of nums -1. So I'm just going to write this binary search here. While L is less than R, we calculate a midpoint. And this is the part I messed up. So it's L plus R, integer division 2. So I did R minus L. You could also do R plus L because addition is commutative. But yeah, so I basically had a minus here instead of a plus. So that's not how you get a midpoint. This is how you get a midpoint. So now there's 3 cases. So if nums of m equals our target, then we've found our answer at index m. So what do we return? Yeah, so we would return m. Otherwise, if nums of m, so let's say if the target is greater than nums of m, then that means we have to search the right half. So we say we want to move our L. So L would be m plus 1. And otherwise, we'll set R equal to m minus 1. And then here, so this is normal binary search. So this problem has a trick part of it, which is basically do you just return L? So I'm trying to think. So yeah, this works because it's binary search and these two. So our target is 7. So L would be here, and that's what, because M would be here. So for a binary search to fail, I think L and R are eventually the same number, and then L would go up by 1 or R would go down by 1. So my gut is telling me we would just return L. So let's see if that works. No. Is it L plus 1 based on these outputs? Okay. Wrong answer. So the target is 0. All right, so let me think about what's going on here. So if we have 1, 3, 5, and 6, and our target is 0, so L gets initialized here and R gets initialized here. m gets set to, let me just index these real quick. So 0, 1, 2, 3. So this gets set to 0 plus 3 integer division 2, which is 1. So m gets set here. And then our target is 0, so that means r will get set to m minus 1. So r will go here. And then it's still less than, so it'll go here. So did I return -1? No, I returned 1. So L, okay, so now it's going to be 0 plus 0, 0, and then 0 is going to be less than 1. So because it's less than, that means we want to move r over. So is it, and then let's say if it was 2, then we would move, so that means we would move L over, and we would want to return L. So I think we want to return, so I have L plus 1, but wouldn't we move, L would go over, and then we'd actually want to return L. So why is L plus 1 working? Let's look at, so if we have 7, wait, this was 2. So L goes here, and then L, okay, so we have L and R. 3 is greater than 2, so we need to search the left half, which means R goes to here. And then 1 is less than 2, so that means we need to search the right half. And to do that, you move up L. Well, first M would go here. And then we would say L needs to go here. And I'm returning L plus 1. So shouldn't this, so why is my code giving me the right answer? So is L actually 0? Oh, because when L, wait, do I say that? And then did I just get lucky or something? Because when they're the same, you still want to search it. So you still want to search it, because then L should go here. So I want to return L. So I could say if target is greater than nums of m, then we should return L. So if target is greater than m, L went up by 1, so we should return L. Otherwise, we should return R. So in the case of 0, right, 0 would make us move R because we want to search the left half. So it would go to -1, but that's not right either. So do we just return L always? Let me try with these changes. We're just returning L and see what errors that gets us. Okay, so my initial gut was right. Okay, so this time I missed the less than or equal sign, but that one's pretty obvious because you can think if I have an array of size 1, I still want to be able to binary search it. All right, so that's problem 4. Length of last word, let's try this one. Given a string S consisting of words and spaces, return the length of the last word in the string. A word is a maximal substring consisting of non-space characters only. Okay, so my instinct for this would be return s dot split. This would be my guess. So you would split it. All right. So that's problem 5, is that? Yeah, that was 5. All right. Plus 1. Oh, is this the linked list one? No, this one's not linked list, but okay, yeah. So basically you're given an array and you have to add 1 to it and then return it. So the tricky part here is if you have a carry, like a 9 basically. So okay, so if you're given this, so if it's not a 9, then you just add 1 here. If it is a 9, so let's say we have 2, 5, 9. So since it's a 9, you move your index over here, add a 1 here instead. So you make this 0 and add a 1 to the other index. If you have like 99, then you make this 0, add 1 to this index, make this 0, and then if you're at the end, you would have to just add like a 1 there. So what's the most efficient way to add a 1? To the beginning of a list. Do you have to do it in O of n? I mean, we could do a cheat and we could say like, we could just keep track of, because really the only case that would be O of n is when you have to add a new digit. And the only time you have to do that is if you have a string of 9s. So you could keep track of, so like this would just be linear. If you have, so to put it more mathematically, if you have a digit x, so like, okay, if you have a digit x, which is a non-9 digit, and then you have any combination of other digits, they could be 9s or whatever. So like digit 1, digit 2 to digit n, this will be linear. But if x is, okay, yeah, so let's define it like this. So we have digit 0, digit 1, digit 2, all the way to digit n. So if digit 0 is 9, okay, let's say if digit 0 does not equal 9, then it's O of n. If all digits are 9, then it's O of n squared, because we would have to do this. Well, actually, it's not O of n squared, actually. It's O of 2n, because we're only inserting one thing. So it'd be O of n and then another n. So all right, so how would we do this? So I would probably loop through it backwards. So I would say for I in range length of digits minus 1, minus 1, minus 1. So digits is a list of integers, right? And can we just return digits again? Yeah, all right, sweet. So if digits of I does not equal 9, Then we just digits of I plus equals 1, return digits. Otherwise, so this is our base case essentially. So if it ever doesn't equal 9, we just add 1 to that and move on. Otherwise, we say digits of I equals 0. And that's it, I think. So we set this one to 0 and add 1 to the next digit. So like, hey, this is a 9. Let's just make it 0 and can do the same thing for the next digit. So the only problem is if I gets to the end. So if digits of 0 is a 0, and can we assume, yeah, it does not contain any leading zeros. So if digits of 0 is 0, so that's like the all 999 case. So we can say digits dot insert at index 0, 1. So that should work. I'm not returning digits though, unfortunately. And this is, it is O of n, but it only happens once. Yeah. Okay. Perfect. So that's +1. We're looking at an hour 7. Wow, I can't believe this is the most efficient way. But if you have to do it in place, then I guess this makes sense. All right, I'll look at, so that's 1, 2, 3, 4, 5, 6. I'll look at one more. Yeah, I'll look at one more. So add binary. This will be the last one for today. Add binary. Return their sum as a binary string. I'm gonna assume that we're not supposed to like just convert them to binary, and then because couldn't we? Let me try doing that first. So if we just, can't we do bin command? I don't know if you can take bin on a string or if you have to do it on an integer. Yeah, okay. So we could say int of a, so it would be bin int of a plus bin int of b. And then turn that in. Let's just put that as result and print it. I want to see what that does. My output is all right, let me try this. It might be concatenating them. Print A and B. I don't know if there's just a method in Python where you can add them together. So we have 1, 0, 0, 1, and 1. So why is... Oh, I see. It's because I'm converting... So 1, 1 is being read as 11 when you cast it to an integer, and then I'm converting it to 11. All right. All right, so let's do it the real way. I'm sure you could. Actually, I don't know. All right, so let's do it. So 11 and 1. I'm gonna do this example. So if I recall how you add binary, so it's very similar to the last one. So if it's 0, 1, then that's 1. So you do this, and then here this is 2. So you do this. This is 1. This is 2. Okay. And we want to return it as a string. So to me, a very flexible way of doing this would be, honestly, we can do it in a really similar way, I think. So we'll say for I in range length, and they're not going to be the same length, right? So we could say like L equals the max between length of A, length of B. Well, I think it would be smart. So if we have something of variable length like this, we should add leading zeros probably, just to make things easier. So yeah, we could definitely just convert these to, so I could say A equals, you know, something like this. Actually, I don't even think I have to say that. Can I just do this? Can you call the list function on a string? Does that work? Yeah, okay. So I'm thinking we'll make them into lists, and then max length will be equal to the max length of A. Let's say if length of A is greater than length of B, they'll say max Alright. So the max number would be A, and the max length would be length of A. Otherwise, max num is B and max length is length of B. Alright, so what I want to do is add leading zeros. So this isn't, so I could insert it to the beginning n times, which would be n squared. I'm wondering if there's some way I could like do it in reverse, or I could just make them queues and just append to the beginning in O of 1. Okay, so what if instead we wrote these in reverse and we said 1 0 1 1 and 1 1, and then we added them here, and then we just looped. Oh yeah, that's actually a way smarter way to do it. So we're gonna reverse them. I forget, is it reversed? Okay, so let's see if they're reversed correctly. List reverse iterator has no length. There's like reversed. I could say. So I could say this, I guess. -1. So this should manually reverse them. So A is 1, 0, 1, 0, so that reverse should be 0, 1, 0, 1, and then B should be, this doesn't look right. That does not look right. Okay, let's just make sure that I'm wrong. So A, why is this not 1, 1, 0, 1? Is that not what it should be? Do I still have A? Yeah, I still have A. That's what I thought. Okay. Copy and paste error. So now it should work. 1, 1, 0, 1. Perfect. Okay, so now what I want to do, now that they're reversed, I want the little one, I want to append that many zeros. So min list would be B and min list here would be A. So for I in range, I guess I could say I equals, I guess I could say like K equals length minus length of B. So for I in range K, and then if it's 0, it won't do anything, so that's good. Right? If I say for I in range 0, yeah, I think that will, I actually have never tried that, I don't think. So I'm guessing it will not print hello. That's what I'm hoping it does. All right, and if I make it 1, yeah. All right, that makes sense. Okay, so I want to say for I in range K, min list dot append 0. Yeah, so now it's 0, 1, and 1, 1. So this is the most significant bit, and this is the least significant bit. All right, so we did the leading zeros. That's fine. All right, so now we'll say for I in range length of either one, because they should be the same. And we'll start with the least. So if A of I equals 0 and B of I equals 0, then, all right, and I guess we'll have like result. Which will be x times result of I will equal 0. So if they're both 0, then it's always going to be 0. Or if they're both 1, and we also want carry. Yeah, so I wonder if these should be ints. Because if we add this one plus carry. Yeah, let's make them ints. And here we'll just append the integer 0. All right. Let's make sure this is working. Okay, A should be 0, 1, 0, 1. B should be 1, 1, 0, 1. All right, looks good. All right. So now we want to check. So if So there's kind of like three cases, or maybe more. So we have 0, 0. Okay, so it could either be so there's four combinations where it's like the digit and then carry. So if the sum, so we could just say like s so digit, let's say total. Okay, so if total is going to be equal to carry plus a of I plus b of I. So that's like the sum. So like if we have 1, 1 and a carry, then that would be 3. If we have, 1, 0, 1, for instance, that would be 2, and etc. So we need a carry if it's greater than 1. So if total is greater than 1, carry equals 1 for next time. Otherwise, carry equals 0. And then the digit, so if total equals 1 or 3, then digit equals 1, otherwise digit equals 0. So we could do it this way. We could also say if total equals 0, then digit equals 0 and carry equals 0. This way it just makes more sense because there's going to be more lines. It's going to be like, it's just going to be more lines. Okay. And then, so for digit, we want result of I to be equal to digit. And that's it, I think. And then we can check if we are done, if carry, then we'll say result dot append 1. Well, yeah. Result dot append 1, and then I think we just so let's print result at this stage. So this is still backwards and integers, so we need to reverse it and then type it, cast it into strings. So result here is 0, 0, 1, so 1, 0, 0, right? And then result is 1, 0, 1, 0, 1, 1, 0, 1, 0, 1. Okay, so it looks good. So what I want to do now is basically just typecast it into strings and do it in reverse order. So we can do that with list comprehension. So I for I in range, length of result. So we're just going to do this thing again, but with result and to a string. Okay, so that should do it. And we have to join it together. All right, it's really slow. Makes sense. I'm doing a lot of like type conversions and stuff. Yeah, that's fine. All right, so I'm gonna leave it there. So I did 1, 2, 3, 4, 5, 6, 7, 8. So I did no way. I did 8 problems. 1, 2, 3, 4, 5, 6, 7. 7. Okay. So I did 7 Honestly, if anything, I felt like I should have done a lot better on them, to be honest. Um, but I think it's good for me to kind of revisit like more simple problems with strings and arrays, because I've spent so much time in like dynamic programming and graph world. So it's good to kind of go back to these and just, think um, how to do them and stuff like that. So yeah, thanks for joining me today. I might do something similar tomorrow. It's it's good practice, and it's also nice to just solve more problems and just get experience to a more breadth of problems and just more problems in general. But yeah, thanks for watching. Today was day 51, and I'll see you guys tomorrow for day 52.